Welcome back. Welcome back to the part four, I guess. Yeah. So we'll be reading the testing blog now, testing chapter. We have completed three chapters of this blog. Now it's the part four. I don't know if it's the video four. It's the part four now. So let's start with no breakpoints. Uh, so testing. Let me set up right. Testing for testing, this post explores unit and integration testing in no-std executables. We'll use Rust support for custom test frameworks to execute test functions inside our kernel. Report the results out of QEME. We will use different features of QEME on the boot initially. Oh, so for the Rust support, we will use the Rust support for custom test frameworks. Okay, we could do that. So for results, you have to know more features on key and you boot initially. I don't understand this language. Now we're gonna do, yeah, we're gonna run time testing in Rust. I can't just test. Can I write test in Tailwind? Oh, sorry, what the fuck they will say in TypeScript? I guess. I'll be bored mode if I'm writing tests in Tailwind. Requirements. This post replaces the now depreciated unit testing and integration test. Oh, what does it say, big bro? We need to have a config toml which sets a default target. Yep, we have a default target and defines a runner executable. Yep, we have that as well. So yeah, you're all set. Now let's start testing in Rust. Rust has a beautiful build. Sorry, Rust has a built-in test framework that is capable of running unit tests without the need to set everything up. Just create a function that checks some results through assertions and add the test attribute to the function header. Then cargo test will automatically find and execute all test functions of your code. That's crazy shit, man. It's nice. So we can write test in any file we could, man, and just cargo test it and program. It's kind of easy. Enable testing for our kernel binary. We can set the test flag in the cargo.toml to true. Okay, cargo.toml test. What we need to do is in the bin, it's like test true, bench remains false. The bin section specify how cargo should compile our block or is executable. The test field specifies whether testing is supported for this executable. So the bin is quite important. Package is this package is just uh package is normal use. If I change it over, it does work, right? It's just naming convention. In the first post to make the test field specifies whether testing is supported for this. We set test equals to false in the first post to make REST analyzer happy. But now we want to enable testing, so we set it back to true. And unfortunately, testing is a bit more complicated for no STD applications, such as our kernel. So it will be hectic. The problem is that the Rust test framework implicitly uses the built-in test library, but we don't have that, which depends on the standard. Yeah, which depends on the standard library. This means that we can't use the default test framework for our new STD command. You can see this when we try to run cargo test in a project. It's run cargo test. I guess this works. Mine is stuck. It's not even building anymore. It's stuck. The error is duplicate lang item in the code. There's something can't find create for test. There's something I didn't get the same error. There's some lang item error shit in this. Uh, am I even recording? Yes, it is recording. So since the test crate depends on the standard library, it is not available for our bare metal data. While porting the test crate to a university context is possible, it is highly unstable and requires some hacks, such as redefining the panic map. We need to redefine the panic map. Oh, we'll be using custom test frameworks instead of redefining the panic macro. Let's see that. Fortunately, Rust supports replacing the default test frameworks through the unstable custom test framework feature. This feature requires no external library and thus also works in no standard environments. It works by collecting all functions annotated with a test case attribute and then invoking a user specified runner function with the list of tests as an argument. Thus, it gives the implementation maximum control over the test process. What it does, it works by collecting all functions annotated with this attribute and then invokes a user specified runner function with the list of tests as an argument. Or so we need to give this attribute to our functions, and then we need to create a runner function which where we have to pass all as the arguments. How do we do that though? Let's see. The disadvantage compared to the default test framework is that many advanced features such as should panic tests are not available. What does should panic do? In addition to checking running values, it's important to check that our code and other conditions as expected before the control guess. What does should panic do? Man? For example, and for the after the test, before the test, after the test, we get. So it's kind of a feature it's known for. We can't use this feature. Instead, it is up to implementation to provide such feature itself if needed. Yes, should panic is like something should panic and we should ignore that, something like that, or it is like uh, it's like self, right? It should panic, so it must be true. It should panic, then you throw another, something like that. Uh, yeah. So this is ideal for us since we have a very special execution environment where the default implementations of such advanced features probably won't work anymore. For example, the should panic attribute relies on stack unwinding. Oh, we don't do that here. Stack unwinding causes to create a different pathway. Stack unwinding causes to do this, right? Implement the buffer. We don't have the memory for that. Um, so we are not doing that way. We are going far away from stack unwinding. Which allows to catch mechanics which is disabled for our kernel. Yes. To implement a custom test framework for our kernel, we add the following to our main.rs. So main.rs, yeah, it is. Oh, where do I add it? So it's done. And I guess there's a feature custom test framework, framework. And the same for, so it's going to be test runner, the create. So, yeah, many functions. Then we have to, I'd like to make it now full start. Yeah, let's see. Full start. And then CFG. This is a test, my man. Function, which is gonna be location, location, or does dynamic mean FN? Oh, oh, so this is argument. So that's a shady as fuck argument. And then running test, test document. I've been writing uh, Java lately. Keyboard, solve this as well. So without without the test runner function quite well. It does it. Let's see what it does. Our runner just prints a short debug messages and then calls each test function in the list. So this is the debug function, and now it calls. What does it do? Yeah, it calls each. That's what it does. So basic for loop. Now the argument type is a slice. So it's a slice of a trait object reference of the function trait. It is basically a list of references to types that can be called like a function. Since the function is useless for non-test runs, we use the CFG test attribute included only for tests. Oh, so this argument is a slice of all the functions. Now, here, how would we define that these functions are of test? So that's why I use the test attribute here, which helps us to only uh, derive, only derive or give reference to functions which have the test attribute. Okay, so yeah, let's try it reads. This reference, so it's a slice of traits, and the traits are a function type, or it's a function tree. When we run cargo test now, we see that it now succeed. If it doesn't see the node do. Let's see cargo. Most I'm sure. Yeah. However, we still see no. There is currently a bug that leads to duplicate line item errors in cargo test subcase. Question your set panic abort for a profile in the cargo. Try removing it, then cargo test should work. Sorry, wait, wait, wait. So there are some different errors now. Nah, error persists. Why? Should do this, then it would work. Sad, panic, abort. But mine is fading of some different issue. Let's see. See if it will, see if it's still. So mine doesn't cause me. These are some different bugs. Let me fix this up. Sorry, people, guys, there was not so much error. It was a syntax error by me. Yeah, a Greek scientist also does that. It's kind of late. I'm dumb, bro. Yeah, so it does work. The reason of now I'm reading in the third line of the paragraph. The reason is that our start function is still used as an entry point. The custom test framework's feature generates a main function that calls test runner. But this main function is ignored because we use the no main attribute. Yeah, writing our own entry point. To fix this, we first need to change the name of the generated function to something different than main. Let's see if I add back that. If I still I can write over here. Let's see if this works. Yeah, this works. Oh, let me just remove graph from there. Just see if it still works as well. No, this kind of fixed the issue for me. This fixed the issue for me. Yeah, that's, let's do it. So what do we need to do now? To fix this, we first need to change the name of the generated function to something different than main. Throughout the through the re-export test harness main attribute. Then we can call the rename function from our start function. What would this do? To fix this, first you need to change the name of the generated function to something different than name. Yep. Yeah, okay, I get that. So we can do this by the re-export test harness main attribute. Copy this. Uh, so what it is a re-export test harness main, and it will give us test main to something in a function from our start. We set the name of the test framework and the function. Oh, we need to add this inside the start. So now we need to add EFT test. Oops, syntax error, CFG test, and then test name. Call the function. Okay, so now how does it know that test runner is this one? Don't know. When we now execute, no, so it's explaining this. We use conditional compilation to add the call to test name only in test context because the function is not generated on a normal run. What does this mean? We use conditional compilation. What is conditional compilation? Rest is a specific attribute. Oh, okay, okay. I'm sorry for that. To add the call to the test main. Yep. Only in test count. What are you explaining this to me? I'm just so confused. Yeah, I got it. When we now execute cargo test, we see the running zero test messages from our test run. Cargo test. That's clean. That's clean as shit. In order to recreate a first test function. So it's not clear how it's doing this. So it's so probably this is the function's name and now they're changing this to this. This is what the function name looks like. Maybe not sure. So now we can write our test cases. Where do I write the test cases? Just before, just after this. So let's write test cases. Case we can write. So we are going to write trivial solution. I'm going to print something. So we can use assert as well. Oops, sorry for that. Assert. Will this work? Should work. Should work. Why are you printing? Printing. Okay. With Cowardice now we see the following input. This right. Okay. Let's see. It has GG's guys. So we are now able to call a function and give it a test case attribute. So it would be a test case now. If the assert equal to assert equal. How do we do like this? I wrote test cases like 2 or 3 months ago. So, oh, it has time. Time, time. Nice. The test slice passed to our test runner function now contains a reference to the trivial assertion function. From the trivial assertion output on the screen, we see that the test case has passed and that it has succeeded. After executing the test, our test runner returns to the test main function, which in turn returns to our start entry point function. At the end of the start, we enter an endless loop. Yep, because the entry point function is not allowed to return. This is a problem because we want cargo test to exit after running all tests. Oh, yeah. So we need to return something, but as it's a dangling function, it won't return something. So how do we do that now? Because of course we need to call it in the start function. So are we not returning it? So now we specify. So executing QEMU. Right now we have an endless loop at the end of our start function and need to close QEMU manually on each execution of cargo test. This is unfortunate because we also want to run cargo test in scripts without user interaction. A clean solution to this would be to implement a proper way to shut down our OS. Unfortunately, this is a relatively complex because it requires implementing support for either the APM or ACPI power management standard. Luckily, there is an escape hatch. QMU supports a special ISA debug exit device, which provides an easy way to exit QEMU from the guest system. Okay, to enable it, we need to pass a device argument to QEMU. We can do so by adding a package of metadata.putImage.test arguments configuration key in our cargo.com. So we need to do a lot of power management stuff to shut down the OS, which is like closing the QEMU. Or we can do that by easily using the debug exit device, which is already written for us. And we just need to pass it. To enable it, we need to pass the device argument to QEMU. So where did we initialize QEMU? It was in our cargo atomic. So in dependency, what do we need to write? To write this. Copy all of this. Let's station top package the metadata dot boot image. This is device. We added this. We did this. Input of base floating 4 and input of size. That's this. The boot image runner appends the test arguments to the default QEMU command for the test executables. Okay. For a normal cargo run, the arguments are ignored. Why? Together with the device name this, we pass the two parameters IO device, yes, and IO size that specify the IO port through which a device can be reached from a kernel. So a kernel will be reaching to this device, which then talks to power something like that for shutting down our QME, our OS. Uh, and for normal cargo, this will be ignored because the boot image runner appends the task arguments to default QME, and which and the QME commands for the test executables. Okay. We can normally ignore this for a normal run. So let's read about the IO ports. There are two different approaches for communicating between the CPU and the peripheral hardware on x86. Memory mapped I/O and port mapped I/O. We already have used memory mapped I/O for accessing the VG test buffer through the memory address. Yes, so it's a mapped I/O, which is a screen, for example. The address is not mapped to RAM but to some memory on the VGA device. Yeah, this address is for the device and not the RAM. That's understandable from blog sorry, from the chapter one or two. I don't remember the number. In contrast, port mapped I/O uses using a separate I/O bus for communication. What is a bus? It's a electronics term bus. Each connected peripheral has one or more port numbers. To communicate with such an I/O port, there are special CPU instructions called in and out, which take a port number and a data type. Yeah, so IO base is the data type and IO size is the port number. That's why I'm inheriting from this. There are also variations of these commands that allow sending a U16 or a U32. The ISA debug exit device uses port mapped IO. The IO-based parameter specifies on which port address the device should live. The IO-based parameter specifies on which port address the device should live. What does that mean? Yeah, it's simple. It's which takes a port number. So it's a IO-based is the port number, and the port number defines as the address where the device should live. So 0xF4 is a generally unused port on the x86 iOS. I was totally wrong. This is the a number and this is the uh, data byte. Data byte. Oh, okay. It was data byte, no data type. No, it's understandable. Sorry for that. So we are using an unused port as our device port, and IO size specifies the port size, which means 4 bytes. So this means 4 bytes. Okay, it's understandable now. It's in hexadecimal encoding or something. So, so using the exit device. The functionality of the ISA debug exit device is very simple. When a value is returned to the IO port specified by IO base, it causes QME to exit with exit status. Value is less than 1 or 1. So when we write 0 to the port, QMU will exit with exit status equals to 1. And when we write 1 to the port, it will exit with exit status 3. What does this equation do though? I can't really map out it. Why does it go from 1 to 3? Mm, I'll use Copilot. I have a chat here. Chat option. Start a new chat. Name this. Oh, it's taking too much time. Instead of manually invoking the in and out assembly instructions, we use the abstraction provided by the x86 for trade to add a dependency on that trade. We added a dependency section in our cargo.toml. hexadecimal. That's 64. How it's 100. 0.14. I guess it won't much matter because we're just using the IO assembly instructions. Yeah, because the answer. The ISA device actually devices are QMS. Yeah, I get it. When you write a value to the port, like this, the QMU calculates the exit status using this. Example, let's trace the example. Step one, left shift. Oh, it's a left shift function. Now I get it. Now I get it. So left shift means you go one becomes two, right? One becomes two, like something like that, right? If you left shift zero by one, it doesn't do anything. If you left shift zero by one, step two, zero or one. But why? Oh, so these are binary operations. Now you bitwise OR it, so one is the answer out. Now you do one. You shift a left shift it, so it's gonna be two. Now if you two or this, the bitwise OR with this, now it is a OR, so it's get added up, so it's three. By this formula shows the all exit codes are OR do the test. Success versus failure distinctions. Typically, exit code 1 indicates failure, while codes like 3 can represent different test output. Thank you for that. Now we can use the port type provided by the crate to create an exit QEMU function. Let's go back to our main RS and let's create. uh, We should create another function for this. I don't know why I'm not doing this. So let's do derive debug clone copy. I'm so bad today. I don't know why. We have partially to and then we have EQ. So it takes only the U32. Now creating an enum. What would this enum be? So it's mapping all the exit codes. Like the copilot told us. So for success, you'll have all. You have 10, and for failed, why do we do this? You have 10 bytes and fail, we have 11 bytes. Why? Sorry, I'm just lazy. I'm laying down like that. That's it. Okay. Yeah, we could just pass the exit code. Exit code. Let's deal with this. Now you're going to use the x86. Uh, what we're going to use? We're going to use the port function instructions port, and later we're going to use the port. This gives us we need to write unsafe rust again. What we're gonna play with pointers again. It's a port, which is gonna use the port, which is gonna be new, and we're gonna pass the port number. Then we write to the port. Why mapping around there? So what's unsafe in this? Is this port unsafe? I don't know. The function creates a new port at this location, which is IO base of the ISO device, ISO debug exit device. Then it writes the parsed exit code to the port. We use oh yeah. So now the port gets the exit code. So this uh, function gives us this function gives us what? So this script gives us what? This gives us the parsed exit code to the port. Use U32 because we specify the IO size of the ISO device as 32 bits. Both operations are unsafe because writing to an IO port can generally result in arbitrary behavior. To specify the exit status, we create a QEMU exit code event. The idea is to exit with the success exit code if all the tests succeed and with the failure exit code otherwise. The enemy is marked as REPR. Yep. It represent each event by U32 integer. No. Yep. Yes. Sorry. Use the exit code this for success and this for failure. The actual exit codes don't matter much as long as we don't clash with the default exit codes of QEMU. For example, using exit code 0 for success is not a good idea because it becomes after the transformation, which is default exit code when QEMU fails to run. So we cannot differentiate a QEMU error from a successful test run. Then why do we need to map it to QEMU? If that's the case, we can just directly run away from QEMU use exit codes. We can now update our test runner to fit QEMU after all tests have run. We will do our test runner and it's right exit QEMU and pass the QEMU. Oh, we haven't rolled the exit QEMU function though. Any cargo in this now? We wrote it. We just wrote it. I'm down. Cargo test it now. Why? Wait a second. Oops. I always do syntax errors. It's so bad. Mine ran, but the test failed. The problem is that the cargo test considered all error codes other than zero as failures. But we get the one error, so like we need to change it. So now let's just change the success exit code. To work around this, boot image provides a test success exit code configuration key that maps a specific exit code to the exit code. Our dependency is increased. So this we need to add uh, the test arguments. So now it's the test success. exit code as 33, which is oh so it's left shift of the I just remember we read it somewhere. Yeah, this is here. So it's left shift the 10 byte. So what's 10 byte? Left shift 10 bytes by one place. It becomes it becomes 33 somehow. Oh, so now 10 bytes is left shifted, which makes it 32, and then as an OR, this is plus. This is how it works. Let's see. What's this? If there is an EA line, okay, it flew. And now, it's not. Yeah, it's hexadecimal. I know that. With this configuration, boot image maps our exit code to exit code 0. So that cargo test correctly recognizes the success case and does not count the case as failed. A test and an item closes to and it will count as results. Let's see. But that's not obvious. But it does not suffice to read results. It would be nice if we could print the test results to the console so we can still see them after it's done. Printing the console. To see the test output on the console, we need to send the data from our kernel to the host system somehow. There are various ways to achieve this, for example, by sending the data over a TCP network interface. Oh, so it's something nice and we are reading now. However, setting up a networking stack is quite a complex task, so we'll choose a simpler solution instead. Because I just got excited. Serial port. A simple way to send the data is to use the serial port. And my question is still not answered. This query, why did it make it question? Let's just, I am gonna ask you. Why is it 33? Just give me a straight answer, man. So this is 16 because 10 bytes is 16? It's not. Right. In decimal, 10 bytes is 16. It's hexadecimal. Okay. The value 16 shift is 32. And then how is this in? I have to read hexadecimal. I guess I'll read it. I'll read it. I'll read it tomorrow. Yeah, it's come back. Serial ports. Simple way to send the data is to use serial ports, an old interface standard which is no longer found in modern computers. It is easy to program and tune. You can redirect the bytes sent over serial to post standard output or a file. The chips implementing a serial interface are called UARTs. There are a lot of UART models on x86, but fortunately, the only difference between them are some advantages we don't need. The common UART today are all compatible with the 16550 UART. So we'll use that model for our testing. So how does this work? There is a simple way to send. It is easy to program QMU, which can redirect the byte sent over serial program, and QME can send QME can redirect the bytes sent over serial to the host's standard output or a file. Oh, QMU can redirect the bytes sent over to serial to our console. That's what we are trying to focus on. We're using the 16550 UART. Wikipedia about it. Universal asynchronous receiver transmitter. Use universal asynchronous receiver and transmitter. So we'll use this model for transmitting. We'll use the UART 1650 create to initialize the UART and send data over the serial port. To add it as a dependency, we update our cargo.toml and main RS. We have to this where dependency. It's very heavy now. Lot of dependency. UART 16550 create contains a serial port struct that represents the UART registers. But still need to construct an instance of it ourselves. For that, create a new serial module with the following content. Let's create a new serial module now. Yeah. So now let's create a serial module. It's important in the top. Yeah, important top module. Let's create a serial. Start a chat now. It's over there. Uh, I need to get serial RS. Let's get serial RS. Mm-hmm. Mm, let's copy paste this. Where we did. Like the widget as before, we use lazy static and a spin lock to create a static rider instance. Yeah, yeah, nudge works in statically, like line by line. By using lazy static, we can ensure that the init method is called exactly once on its first use. Like the ISO debug exit device, the UART universal asynchronous receiver transmitter is programmed using port I/O. Oh, so it is also programmed using port I/O. Since the UART is more complex, it uses multiple I/O ports for programming different device registers. The unsafe serial port view function expects the address of the first I/O port of the UART as an argument, from which it can calculate the addresses of all needed ports. We need to give it just a single port address and it will calculate it by itself. Yeah. We're passing the port address 0x3F8, which is a standard port number for the first serial interface. This is standard port number for the first serial. So it's a standard number. We did pass it here. It's unsafe. If I grab it, that'll be unsafe. Now we call it once. We'll pour in it. We use mutex. Uh, we use spin lock. And, so yeah, it's all done. Let's set up we have set our serial dependent to our console. To make the serial port easily usable, we add a serial print with serial print and macros. So let's do that. Try doc hidden right got function print arguments. Others are good. Why is this spaced out? It's, I mean, I use score, 20, I use right. Why is this lock it? Let's right. Our the items. When are you expecting? Expecting, no, expecting serial. The serial is, so this was an expect behavior or something. Now let's pinch to host to the serial interface. This is what we need. Macro export. Oh, yeah, macro, macro export. And I macro reach. Just write stuff and understand. But as a writer, kind of curious about which I write stuff. Don't I don't like copy paste. Dollar crate. What is dollar used for? Yes. No, just mixed it. Oh, it's just copy paste it. I'm just too tired. I'm just too tired. Copy paste this. Oh, I just got so much inferred. I just did. Uh, oh, it's just, and this brings to clean it up. Yeah. So this brings to host. Now we pass an argument. Now we take a slice. Or what do we do? What do we mean by this? When we dereference it, do a create. This is beyond my understanding. The implementation is very similar to the implementation of a print and print element. Since the serial port type already implements the FMT write trait, we don't need to provide our own implementation. And this again, we just use the serial print, and here we use the serial parent, and we just give it a, give it a backslash, and then yeah, there I get it. We use different expression, then you pass another argument in it, and for that we used create CL print. For this, we did the argument. Okay, it's there's no an extra expression. You just do it simply. Just concatenate it with the serial print, and then you concatenate uh, the stuff you print, and then the backslash. If it's nothing, you just print the backslash. It's yeah, I get it. This is very much simple. This is very much simple. Now we can print to the serial interface instead of the VG text buffer in our test code. So let's go to Minaris and use this. The questioner is questioner. Instead of print alone, I could just write serial print. And here is the other test. Yeah, here it is. So instead of this, I could write this. Serial print. And, serial print. No, it should work. Does it even matter? Oh, I just write something up. See, that's another does. But it didn't even got control of. Didn't see anything. Note the serial print macro does live directly under the root namespace because we use the macro export attribute, so importing it through use creates serial print element with not wow. Oh, why printing stuff? I don't know. Do we need to add something to our analysis? Doesn't throw an error, so it means it works. Probably this way we are looking at. QMI. To see the serial output for QMI, we need to use the serial arguments to redirect the output to std out. Oh, so it's not definitely not. So I will like test arguments. Wait, give over it. If we give it CN and std out. Okay. CN and give it std out. The cargo test now. See the typing method. So let's see. It works. Works, it works. Have you completed this? OMG, it's a lot. I'm not gonna complete it today. It's a lot. So yeah, that's all for today. I'm so sleepy. It's 2 already. How much time will we continue? It's 1 hour. It's more than an hour. So yeah, we have completed till we complete. So let's. We did this. No, we did this right now. We know cover we should output diagram. When the test results is to see the output inside memory because our tiny handler still uses print diagram. Instead of this, you can change the session natural session test assertively. Yeah. So we'll do this tomorrow. We're just gonna start from this, and then maybe I could end this up, or this is a long blog. Yeah. So GG's, let's continue and let's never stop learning.